Faster, better, cheaper. Near Shoemaker, the first Discovery-class mission, a mission to the asteroids. On today's episode of End of Mission, I'm Paul, the pressure-fed astronaut, and who are you?
I'm Face of Sarcasm. I'm here.
Are you faster, better, and cheaper?
No, I'm slower, more expensive, and worse.
Oh. Okay.
Yeah.
Wow. So on today's episode, we're going to be talking about the first Discovery-class mission. The first faster, better, cheaper mission. And that's where we'll start.
Yay!
And that's where we'll start with this. Okay. So during Bush Sr.'s administration, NASA Administrator Dan Golden started to push for faster, better, cheaper missions. And, well, he did have a point. This also started during Bill Clinton's term as president as well. So pictured here is Mars Observer, which is part of the Planetary Observer Program, which is a Mariner follow-on, sort of. Right?
Right.
Now, these are supposed to be low-cost missions to the inner solar system. That cost a lot more than anticipated, and Mars Observer exploded.
How much did these cost?
I think they're supposed to cost $400 million, or $200 million, and I think they ballooned to about twice that, to about $400 million.
Okay, so they're about twice as expensive as they were supposed to be.
And it took them years to build. Galileo took 8 years and $800 million to build, for reference.
And then it was thrown under a tarp for however many years.
Yeah. So there was Planetary Observer, and then there was Mariner Mark II, which two main missions were crystallized for it. There was Comet Rendezvous, Asteroid Flyby, which never happened. Then there was Saturn Titan Orbiter and Probe, which you may have heard of.
Yeah, I think I've heard of that one.
Yeah, Cassini. Those were and Cassini was $1.4 billion. Which, but considering what Cassini did, I'd say it's worth it. So pretty much, there has to be a better way.
Yeah, okay.
So JPL, APL, a bunch of these guys started getting together saying, okay, how can we do lower cost missions that are still worth the money we spend on them, right? That are still, get the bang for your buck.
Mm-hmm. And
they looked at the Explorer program. So this is not Pioneer, I think it might be Pioneer 8, or is it Explorer 47? Think ISEE-3. ISEE-3 is an Explorer-class mission. Most of those guys are like tech demonstrators, and they look at Earth's magnetic field, aurorae, that sort of thing.
Mm-hmm.
Those are cheap and cheery missions, and they work. We've been using them forever. We're still flying them, right?
Yeah.
What if you built a spacecraft like that, but for deep space missions, like going to Mars or the Moon? Right?
Okay, yeah.
So JPL and APL, so Jet Propulsion Laboratory, Applied Physics Laboratory, they start working on studies for low-cost space missions, crystallizing on an asteroid rendezvous. Because at this point, about 1993, Galileo had already flown by Gaspra and Ida, right? The only two times asteroids have been visited at this point, but there are plenty of asteroids near Earth objects. And they figured this is a great way to do a test bed for low-cost planetary missions.
Okay, so basically this is like an experiment to demonstrate the viability of doing low-cost Discovery missions. Okay.
They don't call it Discovery until after this, because this is the first one. So they crystallized Near Earth Asteroid Rendezvous, NEAR, around a Discovery-class mission. That's what they named it. So a Discovery-class mission is budgeted for about $150 million, operated under a principal investigator instead of NASA management, and can be flown 3 years after they're picked. So
why a principal investigator?
There's a monograph that I read about this, like a little short book about it. The problem with using NASA management was you have a bunch of different people fighting to put their thing on the mission, which leads to a lot of like subdivisions. Whereas the principal investigator is, okay, we are primarily doing this. You can add your stuff to it.
Okay.
Yeah.
Okay.
Basically, it was making the structure of the program a lot simpler and a lot easier to manage and maintain.
Got it. Okay.
Yeah. And so again, it's missions that cost about $150 million and can be flown 3 years after selection, which is a lot better than, 8 years and $800 million, right?
Yeah. That's a lot faster and cheaper.
Faster, better, cheaper, and they would work, of course, instead of exploding like Mars Observer, right?
Ideally, yeah.
Right. So this is Near, and ignore the statistics on it; those are for the end of this. So this mission is an asteroid and comet grand tour designed by Bob Farquhar, our buddy over here.
Bob who?
Bob Farquhar? He was the guy who did ISEE-3. He's the orbital mechanics wizard.
Oh, okay.
Yeah, we'll keep seeing him pop up. So it's an asteroid and comet grand tour designed by Bob with the goal of entering orbit around 433 Eros.
Okay.
So there's the monograph that talks about all the low-cost measures they did, how they built the spacecraft, how the program was structured. And so one of them that's interesting was they used solar panels, and these are actually the farthest out solar panels used at the time. They went out past Mars.
Oh, okay.
Yeah. Right now, the farthest out's Juno, but this is the first spacecraft to do it. And they're so simple that they just popped into place.
Like, just, boop, there it is.
They're up and they're out. This also means that they have to be pointed at the sun all the time. Otherwise, you have to use batteries, and you don't want the batteries to drain. Keep note of this. And also, one of the things they talked about was, because of this, because the engine, you'll see, is in the middle of the spacecraft. Right? You see it there?
Yeah, right. Yeah, like there, yeah.
Center of mass calculations become very important for the guidance system design. Because, right? Right? Because if your engine fires and your center of mass is off axis from it, you're going to torque and give it a moment and start, spinning. So you got to compensate for that.
Okay.
The electronics were mostly off the shelf and miniaturized due to mass and cost constraints. Mars Observer didn't do that, and it exploded. So, got him.
Yeah. Big L there.
Yeah. Another focus was on reliability, having high margins, right? Because the tighter the margin, the more it costs, the more finicky it is. So larger margins means there's a lot more wiggle room to play with it. And then reduced complexity. So keep it simple, stupid.
Yeah. I mean, yeah, because there are fewer things that could break on it.
Yeah. Then from a management perspective, the goal was minimal staff focused on completing the project. Again, get one guy to design one part under, the organizational hierarchy. And one of the things I read was that meetings for like design updates, just weekly progress meetings, were only 1 hour long.
That's it?
Yep. And if you were giving a presentation, it had to be 3 minutes long.
Yes. Good.
Yeah.
Good. Keep it short, sweet, to the point.
I can attest to wanting not to be in meetings for that long. Oh, man. I
mean, my meetings are like, 5-10 minutes.
Oh, you're lucky.
Yeah.
Mine are long. Of course, Teams doesn't recognize me as signed in anymore, so I gotta fix that. So it also makes meetings really short for me. It's like, oh, I can't join, sorry. Oops, oh darn. Also, the interesting thing was, software for the spacecraft was being constantly updated, even up to 1 week before launch.
Really?
Yeah. So,
dang.
Yeah. And what do you think the launch vehicle is?
Is it gonna be a Delta 2?
Whoa, man. Are you psychic or something?
I mean, see the Delta K upper stage with Star Motor kick stage.
Yeah, well, it's a Discovery class mission. What do you think it's flying on?
I think it's flying on an Atlas Centaur.
Actually, one of the Discovery classes did that, but we'll get there. Here's Bob pointing at the engine, saying, "Look, this is important." And that guy's like, "Yeah."
Yeah, that's Bill Gates going, "Yeah, that looks important."
Yeah, let me update the software all the time.
And it just crashes.
Yeah. So this is Near Earth Asteroid Rendezvous. It's not a very big spacecraft, as you saw.
Yeah.
So you can see the configuration of it. So you have the solar panels here, at the high gain antenna here, and then most of the experiments are actually on the bottom half of the spacecraft, down here.
Mm-hmm.
The aft deck, you got side panels, and inside here is just propellant and the propulsion system.
Right, because the engine's sticking out the side.
Yeah, it's a pretty simple spacecraft. So there's,
yeah, I mean, that's what you want to. That's what you want to have if you're trying to like reduce costs and increase performance, right?
Exactly. So here's the equipment on board. I tried to get the image to look right because it was in black and white, and neither gradient looked really good for it. But I liked this one because it made it look science-y.
Yeah, it's like, this is an imager, the sweet innocent imager.
Yeah.
Until it wasn't.
Yeah, exactly. So there's 6 experiments on board Near. The multispectral imager, which takes like 500 by 500 pixel images. Trust me.
Beautiful.
You can count the pixels on a lot of the pictures we take.
I mean, this was the great pixel shortage of 1993, so what do you expect?
Well, yeah, they just found the imager in some guy's garage. Like, I wasn't going to use this. I was going to throw it out, so here, take it. Here you go. Faster, better, cheaper, right?
Yeah, they didn't have the budget for more pixels.
Yeah. Then we have the near-infrared spectrometer. What do you think that does?
Is it spectroscopy, perhaps?
Wow, the infrared spectrum from Eros, and it's looking for distributions of olivine and pyroxene, which are the 2 most common minerals in Earth's crust. So,
okay, so like, those rocks out in space, are they kind of maybe taste like Earth?
Yeah, are these rocks Earth-like?
Mm-hmm.
Then you have the X-ray spectrometer, which is attached to the gamma-ray spectrometer. So the X-ray spectrometer is using a 3-gas proportional counter to look for magnesium, aluminum, and silicon lines below 2 kiloelectron volts.
Cool, very cool.
Yeah. Then we have the gamma-ray spectrometer. It's looking for potassium, silicon, oxygen, and iron. Also, it was used for gamma-ray readings just in space as it was flying. So it paired up with some telescopes to look for gamma rays. I didn't really find much data on what it did find, but it was also part of that.
Okay.
Yeah. We have the Near Laser Rangefinder, which is really cool looking. And look at that.
That looks like a laser cannon.
Yeah, it looks like a steampunk laser cannon thing. It's so cool. It's doing topography mapping of Eros.
Oh, that's sweet. That's sick.
Then there's a magnetometer. What do you think that does?
All right. No idea.
No clue. It's just they just found it. Somebody just put it on the spacecraft just to get rid of it. I don't know. Then
someone handed them a VCR and they said, "This is a magnetometer," and they're like, "Okay," and just put it on.
Yeah, just found this. It was in my garage with the imagers. Just take it. Why not?
Yeah.
And then we have radio science experiments. So technically there's 7, but they're just using the Doppler shift from the radio signals coming in to look at it, for measuring things.
For measuring gravitational fields.
Yeah, Doppler, that kind of fun stuff. And just messing with radios, I guess. It's got to listen to something on the way, right?
Yeah. It's Cow's 100.9 KOWZ.
Exactly. And
best variety.
And we just doxed ourselves because we know what that is.
Yeah.
So here's Near in the assembly, getting ready to go. A little engine it's got. Oh, and just so you're clear, the little umbrella shape around it, that's a heat shield.
Oh, yeah, I assumed.
Yeah, because pretty much the cooling of those little engines is radiation. It just glows, and that's how it cools itself.
That's cool.
Yeah, when we talk about the Japanese Mars mission and the Japanese Venus mission, we'll talk about making sure that doesn't get too hot and melts.
Oh yeah, because don't Japanese engines have a problem of melting at the throat, and then the engine belt falls off?
Yeah, like with was it Slim? Yeah, that was really funny. Oh look, here's the tracking camera. There's the engine.
Oops.
Oopsie.
It's a little too hot there.
Yeah.
Maybe you should make the throat a little thicker on the outside so it doesn't melt.
It just keeps happening to them too. And then look, the launch vehicle. I wonder what this is.
Kind of looks vaguely like a Delta II, but it couldn't possibly be. For a Discovery class mission?
No. That's a Proton.
Oh, okay.
Yeah. Okay. So, our launch is February 17th, 1996 at 3:43 p.m. Eastern Standard Time, almost exactly 3 years after Near was conceived.
Hey, yeah. That's pretty close to schedule.
Yeah. It launches on a Delta II. Wow. From LC-17B at Kennedy Space Center. Wow.
Exhilarating.
I do like the Delta II. Hey, look at that. It's a cute rocket.
It's a good looking. Yeah, it's a good rocket.
It's a good looking rocket. So it's Delta II. It's got a Star 48 kick stage, and the escape burn will be done over Africa. Now, so first they'll go into orbit, do a quick checkout, and then burn. Right? That's how they always do these missions. So there's the Deep Space Network Canberra team, which is in Australia. They were listening for Near, and they couldn't actually detect it. And they were freaking out over this until they realized that the signal was so strong from Near that the antenna just wasn't picking it up.
Oh.
Yeah.
It's too powerful.
Yep. The motor kicks on, it goes out, and it's placed in hibernation for a rendezvous with 253 Matilda in June of 1997. So this is the plan, as you can see here. They launch from Earth, they do a flyby of Matilda. Oh, where's Matilda?
Right there. You were pointing right at it.
Right there. Then there's a maneuver after that to do an Earth flyby, and it's going to go to Eros. There. Okay? That's the plan. Keep that in mind.
Yep, going to Matilda, doing a burn, and then swinging by the Earth and go to Eros. Got it.
Yep.
Got it.
Yep. So here's just a picture of... This is the icon for the mission. It also looks like the Channel Awesome logo, if you remember that.
Yeah. I do remember that, yes.
And for those of you who are too old or too young, apparently, to know what that is, Channel Awesome was a collection of early YouTube review people, like The Nostalgia Critic, Cinema Snob, other people...
Etc.
Yeah, etc. It fell apart. The only one who still does stuff... Cinema Snob still does stuff. I follow him. They all kind of fell apart because more professional reviewer types, not just amateurs who like or don't like certain movies or video games, came into the scene. Like Red Letter Media kind of did away with Channel Awesome. But I had to explain who the Nostalgia Critic was to someone on my Discord once, and they were younger than me, so I had to make sure people know who that was.
Okay.
You know that gif of Matt Damon from Saving Private Ryan where he gets really old? I had that happen when someone said, "Who's the Nostalgia Critic?" Oh no. Also, there's a lot of gifs of him. There's also those.
Yeah, there are. Yeah, there are.
And so then here's the team, and you'll recognize some of the things here, right? Voyager 1 and 2, Galileo, Ulysses, Topex, Poseidon, Mars Global Surveyor, Cassini, Deep Space One, Stardust,
others, etc.
QuickSat, AcromSat, and then actually, this is this mission, right?
I think I do.
That's STS-99. You're doing that one later this year.
Oh yeah.
Yeah. You say, "Oh no." Right, of course.
Of course. Yeah. I knew. Yeah. I knew that.
Of course. So let's go to Matilda. So 253 Matilda was discovered on November 12th, 1885 by Johann Palisa.
Wait, isn't that the exact date? No, it's September. Is it September 12th or is it November 12th?
For what?
That's when Back to the Future 3 takes place.
That was November 1885 because it's always in November, right?
Yeah, it is.
So this is around the same
yeah.
time that Doc Brown hijacked a train to go to the future. At the end of Back to the Future Part 3.
Yeah, to go back to 1985.
Yeah. Very exciting.
Yes.
Also, so this is Matilda. It's a C-type asteroid, which means it's carbonaceous. A lot of carbon in it.
Oh, okay.
Yes.
I thought it was like it sucked at math, and so it got a C grade.
It's a C. So there's C-types, S-type, which are stony asteroids. There's M-type, which are metallic.
Okay.
Yeah, that's kind of
so stony, carbon, metallic.
Mostly, yeah.
Okay.
Yeah, because like the C-types have a lot of like carbon, hydrogen, oxygen in those. They're like mud balls. Stony ones are just rocks, and the metallic ones glisten. You know.
Ooh, shiny.
So this one is 66 by 48 by 46 kilometers across, so about 42 by 30 miles. This is actually the second largest asteroid visited by a spacecraft ever.
Dang,
That's
big.
It is very big. Its orbit's 3.35 by about 2 AU, so its year is about 4.31 years on Earth, and its day is about 17 days long. It's really slow rotating.
Oh, wow, okay.
Yeah.
Dang.
It's a really slow rotator. The flyby took place on June 27th, 1997, at a distance of 1,212 kilometers, so about 753 miles, and at about 10 kilometers a second, right? It's going...
It's zipping past.
Now, taking pictures of Matilda is pretty hard because look at it. You'll notice some distinct features on it.
It has, like, craters and lumps and mountains and...
It has giant craters on it.
Oh.
Yeah. So it's also a very dark surface because it's got a lot of carbon in it. So the albedo, the reflectivity of it, is about the same as asphalt. So like road. That's,
okay. I mean, that's still kind of pretty bright.
Yeah, you can still see it, but you have these giant craters that also negatively influence how you could see it. Right?
Yeah, true. But I imagine that, though, it would help, though, right? Because you have, like, the higher contrast because of the craters, and you got the one side illuminated.
Yeah, but you can... But this is the only side that they saw, because it's just a quick flyby. But you can, it's just... Yeah. Just giant craters. And the craters... So this one, Damodar, is 20 kilometers wide.
Just giant.
Yeah, it's an enormous crater. So the craters are actually named for coal fields. Because it's carbon.
Cool.
Yeah, because it's a carbon, right? Coal is carbon, right?
Yeah. Coal is carbon.
And if you look closely here, if you follow just on this side, you can see a little scarp here.
Oh, yeah.
That's about 20 kilometers across, which means that there's actually some internal structural strength to Matilda. So it's not just a pile of rubble.
Right. I mean, there are giant craters on it, but yeah.
But if you look at like Bennu looks just like a bunch of rocks put together.
Okay. And this has more structure to it because it's bigger, has a bunch of giant craters that impacted this thing, and it's still here, still kicking.
There it is. Yep. So after this flyby, Near makes its way for an Earth flyby to set up the Eros encounter. So this is Matilda.
Oh, okay.
Yes, this is Damodar, of course. But you also can't see inside the crater either, as you can see.
Yeah. It's too deep.
Yeah, it's just there. You could put really big antennas in there.
I mean, sure, you could.
Yeah. We could put giant subwoofer, right?
Oh, yeah, okay. Now I see what you mean.
Get some nice beats going, you know?
Yeah.
You can see the clarity.
Big cup holder.
You can see the clarity of images coming in from Near.
Yeah. Oh, yeah. Oh, yeah. Look at high quality images. Faster, better, cheaper.
Faster, better, cheaper. Yeah. We can see this is a crater. This is a crater. There's some little ones there, but there's a crater. So you have Damodar, there's Karoo there, there's Lorraine. These are all different coal fields and same. And you can still see like there's some structural features here right? Troughs.
Yeah, I see them more clearly in this image, yeah.
Yeah, well, you got time to map it out, but yeah. There's Ishikari, Kuznetsk, all coal fields. Oashka, Mulgildy, Lublin, Baritsa. So, it's nice. That's Matilda.
Yeah. Okay.
So, first, there's a deep space maneuver on July 3rd, 1997. Keep note of this.
Uh-huh.
So there's an Earth gravity assist on January 23rd, 1998, and the closest approach of 540 kilometers. That's where Starlink is at.
Oh, okay. So it's getting real close to Earth.
Yeah, it's got to do a massive plane change maneuver, and if you were in the right spot, you could have seen it, like going across the sky.
Ooh, that would be cool.
That would have been really cool. Now, the orbit change, I think, is incorrect. I think I misread the monograph, so we'll ignore that. But it changes its inclination to 10.2 degrees, because Eros is at 10.2 degrees off the ecliptic.
Got it. Okay.
Yeah. So this is going to set up the encounter and orbital insertion on January 10th, 1999.
All right. All right.
But first, obviously, on the way, you got to make some correction burns, right?
Mm-hmm.
So, on December 20th, 1998, we're getting really close to the encounter. They turn on the main engine, and it immediately is aborted.
Uh-oh, what happened?
And then, Near enters safe mode and starts to tumble.
Oh, no.
As it's trying to save itself, it fires its thrusters thousands of times, which drains 29 kilograms of propellant. Now remember, there's about 700 at liftoff, and they've used a bit of it to do maneuvering. Now,
okay, so they're using some of the tank, but jeez.
Well, we also have to enter orbit, which requires some propellant, right?
Mm-hmm.
Now, remember, Near's solar panels have to be pointed at the sun.
Oh, no.
And, if it doesn't point at the sun, you'll have to use the batteries, and if it doesn't get back to pointing at the sun, the batteries could drain, and you'll never recover. Because the problem is, if you're tumbling at a fast enough rate, sure, you'll charge them for a bit, but they won't be able to do anything. Someone actually found...
Right, because... Sorry, go ahead.
Because someone actually found an old Lincoln experimental satellite, which the batteries had failed, and it was transmitting whenever the solar panel faced the sun, as it was tumbling.
Oh, jeez. Oh, no.
Yeah. So you can see here, right, so the minutes after the aborted burn, the sun angle, so that's how it's pointed at the sun, right, it starts twisting, and then it starts tumbling.
Yeah.
Right? You can see this in the momentum. There's a bit of momentum, and then... and it's trying to correct for all of this, right? And, of course, the bus voltage is dropping steadily, which is not good. And event indicators, that's just like a little thing that says, hey, something's turning on, something's turning off.
Mm-hmm.
So the spacecraft is out of contact with Earth for about 27 hours.
Oh, no.
And no one really knows what did this. We still don't know. But the investigation did find 17 issues that needed to be fixed on Near.
Oh, jeez.
And it did note that there was a similar spike like this in the data of like momentum during the July 3rd burn. So most likely what happened was the start-stop transient overwhelmed the guidance system and it freaked out.
So what does that mean?
So when your engine start, it jolts, right? It's like when you hit the brakes or you accelerate your car, it kind of jerks forward.
Yeah.
Right? Well, you have accelerometers on it, and so maybe the turning on of the engine shook it in a way that freaked them out. Like it entered a resonance mode or it sent a signal that was like, oh my gosh, what's going on? It's kind of like on Conestoga, the first flight, right? There was a vibration on the thrust structure that happened to be near like the resonant frequency of the guidance system. So the guidance system was picking up this vibration as, hey, you need to correct for this. And it was telling the motor to steer when it didn't need to.
Oh, okay.
Right. You could also probably what happened on the ISAR Spectrum first launch, because if you watch that, you'll notice after it takes off, the jet starts like turning, like the engines are steering when they don't need to, and that's why it loses control.
Ooh.
So
Okay.
yeah,
So basically, they fired up the engine, and it probably shook the guidance system so much that it tried to correct for it.
yeah, it freaked out a little bit, and it started tumbling.
That's not good.
So they recover the mission, change their pants, of course,
Yeah.
So now they can't fly by. They can't do the orbit insertion of Eros now because that's like 20 days away. They can't do that now. So instead, they'll do a flyby on the 23rd, so 3 days later, to set up a rendezvous in February of 2000.
Okay. So basically, like 15 months later, we'll try again.
Yeah, because you can't recover that quickly because you have no idea what will happen again. The last thing you want to do is lose the mission, right? At least get a flyby out of it.
Yeah.
So let's talk about Eros. Eros is kind of cool, okay? It's big.
Mm-hmm.
It was discovered August 13th, 1898 by C.G. Witt and Auguste Charlot. French. It's a French name. So that could be anything.
It's actually Chuck.
Yeah, Auguste Chuck. Its size is 34.4 by 11.2 kilometers, so it's a potato, right? Which is about 22 by 7 miles. So, right, you can see how big it is. Now, we know these dimensions more accurately because we've been there, but this is from an early study of it, which says it's about 15 miles. It's one of the largest near-Earth objects. Its orbit's about 1.78 by 1.46 AU, so its orbit is about 1.76 years, and it rotates about every, 5 1/3 hours, so how many minutes is that? It's like 5 hours, 18 minutes, roughly.
5 hours, 18 minutes, yeah, okay.
It spins, it orbits. So it's named for Eros, the son of Aphrodite. It's been the subject of great interest for exploration because of how big it is. It's also the first asteroid detected with Arecibo's radar capabilities as a test to see if it would work, and was actually considered for a post-Apollo rendezvous mission.
Ooh,
Yeah.
okay.
Yeah, so the crew would go up on an enhanced Apollo and do a flyby of it. It's
You're like, wow, look at this. Get some pictures.
Yeah, because the pictures, and we got to tumble first, though,
Oh, yeah, that's all part of the mission.
Yeah. So the near flyby takes place on December 23rd, 1998, so it's near Christmas, so we can all celebrate.
Hooray.
At a distance of 3,827 kilometers. This flight...
It's a pretty big distance.
Yeah, but considering it almost, tumbled and died,
yeah.
you work with what you
Fair.
got. And this reveals the shape of Eros and its stony features.
Ooh, okay.
And if you've seen articles that talk about asteroids, they've probably used Eros.
Yeah, I like the soft glow that it has around it.
Yeah, it's
kind of reminds me of like those 40s or 50s movies.
Yeah.
Christmas movies.
Like those, or like a Star Trek episode, like an old original series episode. And they're always when the woman's in frame, they always have the soft glow on her.
Yeah.
But this is 433 Eros, up close, personal. And that's a really big crater.
Yeah, in full 500 HD.
Yeah. Again, you can see the pixels. Start counting.
Yeah.
So, this is actually a good thing that it tumbled out of control because the flyby allowed the team to actually look at Eros and go, okay, it's a potato. These are its shape. Where's the center of mass? So you can plan how they're going to go into orbit.
Oh, okay.
It gives them some time to kind of... Then, now that you know what the features look like, you can start looking for things to, look for, right? See, there's that big crater, Psyche. We should look at that more than we look at, rocks or whatever, right?
Yeah, there's a big crater, there's a small crater. We don't really care much about the small crater. Let's look at the big crater. Yeah.
So, get ready for another burn on February 2nd, 2000, where then the spacecraft enters safe mode again while preparing for the burn, but they get it to work on the 3rd.
Jeez.
And on Valentine's Day 2000, which, hey, Aphrodite, son of Eros, at 10:33 in the morning, Maryland time, Near enters orbit around Eros.
Yes.
Now, I remember reading in the monograph that something funny happened with the team. This is when they changed from the worm back to the meatball for NASA's logo. And everyone the PAO was, the public affairs guy was talking about how, we want to do press conference here, but there's no NASA symbols. How do we know this is NASA? So the team just printed out an ungodly amount of NASA logos and just put them everywhere, all over the place as a joke.
Dude, will they think that we work at NASA?
Yeah. How are you supposed to know you work at NASA, right? It's like that person that worked at the IT part of where I work. Their cube was plastered with Elvis stuff.
Oh.
Like Elvis paraphernalia. Of course, if I'd seen it, I was like, see, like the Big Bopper, I take it, right? Just as a joke. I'll shut up.
Okay. This is where you gotta wear the company polo with the company vest, drink from the company mug, driving the company car.
Yeah. You drink the mug to make sure the logo.
With a company pen.
Yeah.
Get the company notebook. Yeah.
I always, when I go to work, I always think of my company and the values it has.
Mm-hmm.
So the orbit it enters is 366 by 321 kilometers, 227 by 200 miles. Now,
so it's a pretty high orbit over the thing.
Well, you want to make sure you don't hit it, right? It's a banana.
Yeah.
But over the next year, it'll perform maneuvers and observations of the first ever done up close of an asteroid, and it's going to get really close to the surface. I think the closest approach done was about 5 kilometers above the surface.
Oh, okay.
Which, to put that in perspective, when I run on the treadmill, I run 3 miles sometimes, which is about 5 kilometers.
Yeah.
So
it's getting up close and personal.
Yeah, it'll go to different orbits, to different planes to get we're gonna see Eros. Okay, we're gonna know every inch of it, or every inch, 10 meters.
Every pixel that's available.
Yeah. This Near, of course, is the first spacecraft to orbit an asteroid. Obviously.
That's pretty good. It's pretty cool.
Now, this is when Near gets the name Near Shoemaker. So who's Shoemaker?
Okay.
This guy. This is Gene Shoemaker. He was born April 28th, 1928, and he died on July 18th, 1997. He was part of the original mission planning for Near. He was one of the guys saying, hey, you should go to the asteroids.
Oh, okay.
Yeah. Now, you've probably heard of Gene Shoemaker for Shoemaker-Levy 9, the comet that hit Jupiter.
Yeah.
But if you're a planetary geologist or planetary scientist, he is the guy. One of the biggest names in it. So his first claim to fame is his doctoral thesis, which proved that Barringer meteor crater was in fact an impact crater.
What did they think it was before? Just like a volcano?
Yeah,
volcanic crater?
Yeah, a volcano. They thought it was a volcano. Because remember when we were at the Grand Canyon, which is kind of close to a meteor crater, off to the distance was other volcanoes. They thought it might have been a volcano crater. But what he did, he looked at nuclear testing sites and the craters those made, and he went to meteor crater and noticed similar geology, like specific minerals and rocks. Those rocks could only have been made by a really fast, a high-pressure heat wave. So either the dinosaurs had nukes, or something hit the Earth to make that.
And perhaps that thing that hit the Earth was a dinosaur nuke.
Yes, maybe. I don't know much about the dinosaur space program, so maybe they had SDI, who knows? But he proved that this was a meteor impact. He's the guy. So then his work was with Lunar Orbiter and the Ranger programs, which generated the first geologic maps of the moon, which he did alongside Harold Urey and Gerard Kuiper, who we talked about with Mariner
10, yeah.
Namesake of the Kuiper Belt. He's, again, first geologic maps of the moon based off this data. And then he was the principal investigator for the Surveyor missions, which landed on the moon.
Ah, okay.
Yeah.
So he's big.
And then he was training Apollo astronauts for their field geology when they were on the moon. So this is him leading up the Apollo astronauts at Meteor Crater to train them in geology.
Hey, look, these are the different types of rocks you got to be looking out for.
Yeah.
Right? And here's like the different indicators you got to be watching out.
Yeah, because I remember a story about that. I think it was David R. Scott. I think it was him or someone. Or just all the Apollo astronauts were, why are we learning about all these rocks? This is so boring. I just want to fly the spacecraft. And then by the time they're on the moon, they're like, hey, wait, that's that rock. I knew it. I found it. Look, I got it. I found one of those. One of them was just so excited that the geology he learned was actually applicable to his time on the moon. I can't remember which one.
Wow, look at that. You actually learn about different rocks. That way when you're looking at different rocks, you could go, oh, those are different rocks.
Yeah, you gotta look at these the different rock types. Because again, only one geologist ever went to the moon. And actually...
please tell me that's going to change with Artemis.
Hopefully. Actually, one of the astronauts, she got her degree in mining from the University of Alaska. So...
Perfect.
So we could prove once and for all that drillers can become astronauts as well.
Yes.
And
I thought you were going to say that we could once and for all prove that Alaska is not in fact on the moon.
That's true too. Gene was actually considered as an Apollo scientist astronaut, but he had Addison's disease, which is it's like one of the glands in your brain doesn't work right. I think Kennedy also had that.
Ew, okay.
Yeah, so he suffered from that, so he couldn't fly, which unfortunate. So after Apollo, he focused on discovering and classifying near Earth objects. You can see his interest in this mission and why he was important to it.
Yeah.
And then after that, he went on a worldwide search for hidden impact craters. Right, Meteor Crater's an impact crater. Where are some other ones?
Yeah.
And then when he was in Australia looking for one, he died in a car accident. So,
R.I.P.
That's why I made that very dark joke in Deep Impact, the movie about the astronomer. Yeah. But some of Gene's ashes were put on Lunar Prospector and are actually on the moon right now.
That's awesome.
Which is really cool. See, I think he is actually the first person to have ever been buried on the moon, officially.
Oh, that is sick.
That is really cool.
That is sick.
Again, Gene is a very cool dude. I just did a quick summary of this guy's work. If you like planetary geology, you like Gene.
I like Gene.
Yes, you do. And this is 433 Eros.
Wow.
Look at it. And already you can see some very important features we're going to discuss. Already in these two pictures.
Yeah, you can see like giant, what look like eroded impact craters, like 3 of them.
Here?
And then you got that big one right there that you're circling.
Yep.
And then it looks like we got some other stuff going on in the upper right corner.
So actually this is a crater. Eros is its name. This is a crater. That's
a crater?
Yes, this is Shoemaker Reggio. I think this is Shoemaker Reggio. It's named for the guy.
Uh-huh.
But so this is 433 Eros, and already we can see geology to look at, right?
Oh yeah.
Right?
Oh yeah.
This is a map of Eros generated based off near data, and all of the craters are named for lovers. Fortunio, Cupid, Don Quixote, Taiyu, Lita?
Psyche!
Yeah, Psyche. It's Psyche. Narcissus.
Yeah, Psyche.
He loved himself, but we'll forgive him for that. Fujisobo, Celine, Gamba, Hios, Genji, Catherine, Cupid. So this kind of give an idea of what the geology of Eros. Of course, how do you make a map like this for a potato? I don't know.
Yeah. You try real hard.
Yeah. So on Eros, we find some very interesting geologic features. Shallow troughs, flat floored troughs, fractures, pit chains, ridges, and grooves. It's a groovy place. Right? So you can see here, there's a giant groove. Sorry, not groove, ridge. And actually, I think right here is a vertical drop.
Yeah, that looks like it.
Yeah.
Because there's almost like a little groove right next to it, too. Almost
Yeah.
making it like a little claw shape.
Yeah.
with a ridge.
And this tells you a lot about Eros' geology as well, which we'll discuss at the end. And you can see, look at the craters too. Isn't this interesting?
Yeah.
Well,
so they're like brighter. Is that from like ejecta material, or is it like the?
It's the opposite, actually. We'll discuss that. We have more close pictures of it, and you can see there's a giant crater.
Yeah.
A lot of craters. You also see boulders, different crater sizes. It's a very interesting world.
Yeah.
The first thing you'll notice that I wanted to talk about here is you see this specifically down here.
Yeah, it's kind of flat, smooth, dusty.
That's a dust pool.
Ooh, there's a lot of dust in there.
Yeah, there's pools of dust on Eros. Right there. And you can see there's just dust pools all over the place.
Dust pools everywhere.
And they tell you a lot about the geology of Eros and the activity and what's happening on it. You also see a lot of boulders.
Oh, yeah. I'm looking around, looking at all the big rocks.
So there's dust pools on a lot of asteroids and the moon. I think Mercury has a few. Pretty much if it's got craters, it's got dust pools, which is really interesting.
Okay, so it just kind of like filters in there, shakes, and like falls in, collects.
Yeah, impacts will make, dust fountains, and they'll just settle down in the craters.
And because those are the lowest points, and still have gravity.
Yeah. So you can see more dust pooling here, right? Look at this, like this flattish area. You can see craters that are kind of filled in.
Yeah, and then it has kind of like a zigzag pattern onto it.
Yeah.
It almost looks like it was shaked.
Yeah, and you got boulders, and you can see there's a dust pool and a boulder in this crater here, and even that crater looks kind of filled in. Yeah. And you can see also this, it's moving, it's orbiting.
Yep. Oh, so we're at the Near Shoemaker is close enough to where it's now getting like the motion blur from the orbital speed.
Yeah.
Oh dang. Okay.
Yeah, it's really close. So if you look at we pointed this out in the other craters, right? So you can see they're called albedo streaks in the craters. And you know what causes this?
Yeah. Is it like a heating from the impact?
No. It's dust settling into the base of the crater. So the darker patch here, that's older dust on the surface, and it just sinks to the bottom of the crater, and it exposes the younger regolith and dust, the brighter spots.
Ah,
yeah.
Okay.
So you can see the streaking, right? Because it looks like it's just filling in. It's just
all right.
Yeah, isn't that cool?
Yeah. So basically, the older stuff has been like sunburnt, and it moves in to expose the unsunburnt dust.
Yeah, isn't that cool?
That's neat. That's awesome.
And then this is Himeros crater, the really big one, the big chunk out of it. And this is another shot up close of it too. You can see just the curve of this giant crater.
Yeah,
it's so cool. Then we have Gamba crater. I don't know which one's Gamba. So I actually found the image archive of Near Shoemaker, and it says, "Hey, want to look at this crater? Plug in here, and it'll show you all the pictures it took of this crater."
Dang.
And you can see the troughs too, kind of like the streaks and the waviness of it. And again, boulders everywhere.
Yeah, look at all those boulders.
Yeah, and a lot of little craters. Some of them are filled in. It's so cool. This place is so cool.
Yeah.
And this is Narcissus, which it's the big one. It's the big, big hero of the story. You can see there's more albedo streaks inside of it.
Yeah. It's like, you can see more of the dust kind of pooling a little bit at the bottom.
Yeah.
And then like a Narcissus looking at it themselves in it.
See, Narcissus should have been the biggest crater, the most important one.
Of course.
Yeah.
Of course.
Then we have Don Quixote. I think it's this crater. I think this is Don Quixote. Okay. Which is the first actual novel written in Europe. Right? Tilting at Windmills, that one.
Yeah.
Terry Gilliam made a Don Quixote movie a couple years ago.
Wait, recently?
Yeah, it came out a couple years ago. It's been in production since the 80s. They made a movie about how troubled it was during production. I think it's got Jonathan Pryce and Adam Driver in it. I haven't seen it, so I don't know.
Oh, wow.
Yeah, I don't know if I haven't seen it, so don't tell me if it's good or bad. I have to see it for myself. But yeah, look at and you can also see the value of getting different light sources, right, for the craters.
Yeah, you can see their dimensions.
I think that's Psyche crater, the other big one on Eros.
Yeah, looks like it. It's about that right from the map, from what I remember.
Yeah, and then we've got Lolita crater. We'll keep going then. And then we have Heathcliff, which has my favorite image from this mission. You're taking a picture of me. It's so funny. I knew I had to put that one in when I saw it. This is going in the episode. But you can see like the shape and the impact craters in the shadows here. On like this part here, like these troughs. It's so cool. Such an interesting little asteroid, and it's so interesting. It's a shame I'm not a geologist.
Yeah, it's like there are rocks, there's dust, there's like structural stuff, and boulders and craters.
Boulders and craters. That's what we got here at 433 Eros. Want some boulders? Want some craters? Come on here. I don't know why I talk like that. So we got Taiyu. It's another crater system. I think this is Taiyu right here, or it's the big part here. And you can see it again in shadow. Looks different. All the pixels.
Yeah. So many pixels.
So many pixels to look at. All 10 of them. Yeah, this, again, it's so cool looking at these asteroids up close and just, oh yeah, that's an asteroid. That's what that looks like.
Yeah, it's a lot of craters, a lot of boulders.
A lot of dust.
A lot of dust. Dust pools. Dust pool party.
Wasn't part of the Expanse set on 433 Eros?
Maybe? I don't remember. It's been forever since I saw the first few seasons of that show.
Because I think Ender's Game partially is set on Eros. The book.
Cool.
I think it's the book. This is Leander crater right here. It's this guy. It's one of these craters here.
I like you can see the shadow of the boulder going across it.
Yeah. So cool. And this is Wit Regio. So it's a region of Eros named after Wit, one of the discoverers of it. And you can see the troughs.
Yeah.
And and the ridge there. You can see one of the ridges. I traced it over.
Yeah.
So cool. Pit chains. Again, so many pixels to look at here.
A lot of pixels. And the soft glow helps.
Soft glow really helps. This is Shoemaker Regio. So this is actually, I think, all the boulders came from. Something hit that spot and just spread boulders all over the place.
That was the boulder distribution system.
Yep, hit the boulder factory, sent them everywhere. But you can see the impact chains. You can see troughs. Ooh, look at that. Some ridges.
Look at that.
Some ridges there. Yeah. It is so.
Gonna be honest. The image on the left looks like a nose, like with the nostril.
Oh, yeah, I can see it. Yeah, it's the nose. You took the nose of Heathcliff Crater. There it is. You got my nose. So this is actually what Eros really looks like in color. It's like butterscotch, so it's kind of a brownish tan to it.
Kind of looks like a rock.
Yeah, like a rock. And you can see just the scale of how big this thing is and how big the crater Himros is.
Yeah.
We got Psyche. Yeah, just enormous. Of course, Narcissus, star of the show there.
Of course, Narcissus.
And this is, of course, Narcissus. Here, this is more false color, enhanced color imagery, but you can definitely see the albedo streaks and boulders.
Yeah, definitely like a white and red kind of combination.
Yeah, white, red, tan, brown, and a crater. And some boulders.
A lot of boulders.
Yeah. So this is Eros versus Matilda. You can see how big Eros is compared to it. And you get there's a crater on Matilda. You just put Eros in.
Yeah. Like the thing that created Caru.
Yeah.
Dang. Yeah, sorry. Caru. The thing that created Caru smacked into Eros.
Yeah.
Obliterated.
Yeah. It is so... yeah, we're nearing the end of this, by the way. So, let's look at some science.
Yes.
Important parts. So, there's 9 major science findings from near Shoemaker. Mm-hmm. Tectonic features, pervasive covering of rocks, large spatial variations in density of large craters. There's a dearth of small craters. There's a lot of little pits, but when they talk about small craters, they're referring to small impact craters that look new.
Okay. First, before we continue, I just want to point out that's not how you spell rock.
I know. It's supposed to be.
You don't have an E.
It's supposed to be rocks, and the E and the S are very close.
Sure.
They are. They're right there.
Yeah.
The composition is consistent with an ordinary chondrite, except for there's some sulfur depletion in it.
What does that mean?
There's not much sulfur in it compared to other chondrites.
Oh, okay.
Compared to others.
So the sulfur depleted.
Yeah, there's none there. They're not as much.
Okay.
Structural control of crater formation, evidence of faulting, no evidence for heterogeneity. It's not a pile of rubble, basically.
Okay.
It's largely intact but deeply fractured, likely the fragment of a larger parent body. So it's a rock that broke off a bigger impact.
So it's like one of the parents after the divorce.
Exactly. It's a precursor. So it's a precursor that was primitive, is a primitive body. So I guess, again, Bronze Age civilization was there, I guess.
Right, yeah.
It's not cometary, so it doesn't have like a tail or a coma or anything like that. It's just a rock. Eros is similar to ordinary chondrites, but the definite relationship is not determined. There just wasn't enough data coming from it to say, yes, actually it's a lot like these, or no, it's not a lot like these.
Oh, okay.
It has no magnetic field, and it does not have a moon.
Dang it. Moons are cool.
Moons are pretty cool. I know Lucy discovered a moon around Dinkinesh, I think it was. One of the asteroids it just visited. Yeah. So this is the gamma ray spectra from the surface, or of the surface. So the outer detector is the top row. The inner detector is the lower one. So you'll notice, based off the energies, there's iron, potassium, and silicon. You can see that there. Oxygen and iron. It's a lot more definitive on the inner detector, as you can see. You can see more oxygen and iron, so it's rusted, basically. Oxygen, iron, that composition. Based off of the infrared data, there's pyroxene, olivine, and pyroxene in the surface. It's a rock.
Wow.
It's exciting.
Impressive.
Very impressive.
Very informative.
Yes. The rock is a rock. Yes.
The rock is a rock.
Yep. So, how do you end this mission? Because in February 2001, so a full year later, at that point, Near is almost out of propellant, and the Near camera has failed. How do you end this mission?
You try to get rid of whatever Bronze Age civilization may have been there?
Yeah, you land it. Yes.
Okay.
This actually sparked some arguments with NASA, though. Because NASA was saying, hey, this is not a lander, it's an orbiter flyby mission. You're not landing this thing. And then the scientists working on Near said, but we'll do gamma ray observations of 4 inches above the surface right before impact. And then NASA said, oh, okay, you can do that, I guess. I guess that works. So, on February 12th, 2001, Near lands on Eros. So it's going to come in like that. So it's going to land near Eros, of course.
Of course.
All right, so there's Eros. So it's going to land right about there.
All right.
Yeah, so those cutouts, those are actual images it took on the way in.
Oh, okay.
These images specifically.
Ooh.
So you can see boulders. Boulders.
The rocks has rocks on it. Yeah.
Boulders. And this is the last image taken by Near Shoemaker.
Hence why it cuts off.
So the rough width of this image is about 12 meters, which is about 40 feet.
Okay, so like about the width of a house.
Yeah, about the width of a house.
This is a big rock.
Yeah, and the camera was pointed down. Remember, it's on the bottom shelf. And if they want to get that gamma ray data back to Earth, the antenna has to actually point away from the asteroid. So they land, butt first onto the surface.
Got it.
And I do mean...
So it's looking straight down.
Pretty much. Yeah, and I do mean it lands. It actually survives the landing.
Oh.
Yeah, it's actually awake for 16 days after landing.
Jeez.
Yeah. It was sending back data. It didn't just die. It just... Yeah, so technically this is also the first asteroid lander. But...
Dang.
Yeah. But it was getting pretty cold on the surface. And at 7 p.m. Eastern Standard Time, February 28th, 2001, Near Shoemaker went to sleep forever.
Dang. With its final resting place being on Eros.
Yes, on an asteroid.
That's awesome.
So, needless to say, I'd say Near Shoemaker is a resounding success.
Yeah.
It
feels very much like a Kerbal Space Program mission.
Oh, absolutely. And I'd say, so Near's success, of course, is monumental for asteroid science, right? 2 asteroid flybys, enters orbit on an asteroid, and it lands on one.
Yeah.
But I think the other great achievement of Near is it proved you can do faster, better, cheaper, leading to the Discovery program. Near Shoemaker, Sojourner, Lunar Prospector, Stardust, Genesis? Not you. Messenger, Deep Impact, Dawn, Kepler, Grail, Insight, Lucy, and Psyche, both of which are en route to their targets, and both of them have problems already. Lucy's solar array didn't open all the way. Psyche had a fuel problem that'll be fixed by the time this episode comes out. And upcoming are Da Vinci and Veritas going to Venus, assuming the budget still exists by then.
Wow.
A resounding success for a program.
That is a resounding success. Dang.
The first Mars rover, working Mars rover. A lunar that found water on the moon. Comet sample returns. Solar wind and Utah sample return. Explosion. That's why I did in these colors, by the way. That's the one that didn't work, right? And we've covered Messenger and Deep Impact, right? Just amazing successes. Yeah. And we're going to come up on like Dawn, right? Going to Ceres. Kepler found so many planets. Grail mapped the gravity of the moon. Insight went to Mars. Lucy and Psyche are en route, which actually Lucy, a couple weeks ago, did a flyby of Donald Johanson.
Oh, wow. Okay.
Yeah. And already you see some features you'll recognize. There's dust pooling, right? This asteroid...
Yeah, this looks like it's huge, though. It looks like it's being sucked towards the one lobe.
Yeah, it's 2 asteroids that actually bunked into each other and fused.
Okay, that's awesome.
Yeah. So this one, I think, is about 4 kilometers wide. I think that's how big this asteroid is.
All right.
Yeah.
All right. So it's about the size of a city.
Yeah, it's decently sized. But look at it.
It's got craters, boulders,
you can see some,
dust pools.
Right. That's...
ripples, ridges, fractures.
And we wouldn't know this without the Discovery program.
Yeah.
So, that is Near Shoemaker.
Dang.
Yeah. What a mission.
That is incredible. Going strong out of the gate with a Discovery class mission.
Yeah, except for the part where they almost lost it because of some issue.
Details.
Faster, better, cheaper. Yeah, Dear Shoemaker. This is actually one of the missions that inspired End of Mission, actually. Because I like the look of the spacecraft, and I thought, wow, this is really cool. I'd like to talk about this. I just don't know how.
Yeah, well, it's kind of like a Know Your Rocket, but in this case, it's Know Your Missions.
Yeah, originally it was to be Know Your Spacecraft, but then I gave up on that because that's hard. Now it's End of Mission. Know Your Mission. But yeah.
End of Mission.
Yeah. But yeah, Near Shoemaker. What a mission.
What a mission.
That's why I like the Discovery missions too. It's like these cute little guy spacecraft just doing these really cool missions.
Yeah.
Yeah.
You get to see awesome stuff.
Really cool pictures. Craters that look like going, ah!
Yeah.
Yeah. Any final thoughts on Near Shoemaker?
No notes. No. 10 out of 10.
Absolute cinema. Great mission.
But that, I mean, it definitely also just feels a lot like Kerbal Space Program.
Yeah. It starts tumbling out of control, then you land it and it still works somehow.
Yeah.
On the next episode, STS-54, a TDRS deployment that was picked only because of this image of the crew, which you will recognize all but one of them, because we've seen them all before.
Yes.
Of course. You know which one we haven't seen before?
Of course. I know exactly which one we haven't seen before.
Susan Helms. Yeah, because we saw Casper and Runco on STS-77, and we saw Harbaugh and McMonagall on STS-39. So there.
Yeah, exactly.
Of course.
Yeah. Of course. Yeah. I knew that.
And again, this is the only reason I picked this mission so soon. It's because they're dressed like they're in Star Trek.
They're also at the set of the bridge.
Yeah. And of course, Mario Runco looks like Spock.
Yeah.
You just can't. As the first thought I had whenever I saw a picture of him doing one of these missions in one of those old Scholastic Book Fair books, and I went, what's Spock doing? Oh. So, we'll do that on the next episode.
Yeah. Hey, thank you all, everyone, for watching. And we'll see you in the next episode, because this has been End of Mission.